Hello, folks, and welcome back to session 2 on this day 2 on stage 2. We're all 2s at the moment. So I'm pleased to welcome Ignacio Marré, who's EVP of Operations for 4Subsea, and he's going to talk about motion monitoring of cables and CPS. Ignacio, the floor is yours.
Well, thank you. So thank you for the introduction. And first of all, hi and welcome to all who have joined this presentation about motion monitoring of cables and cable protection systems, CPS in short. So today I'm going to talk about how we use sensors to measure actual in-field motions of cables and CPS to deliver value to the offshore wind industry. So in 4Subsea, we deliver critical decision support to energy providers, and ocean space is our playground, and we deliver our services with a global reach scaled through technology. And I mean, we're a geeky bunch in 4Subsea. We truly believe that technology is the solution to most challenges, but technology alone doesn't really provide value. So we at 4Subsea, we have a high focus on that we need to combine this with a strong understanding of the underlying situation to optimize the challenge to be solved, and last but not least, the situation or workflow where the technology shall be used to support the right decisions at the right time. It is through this that our solutions provide value, actionable insights through data-driven decision support. So 4Subsea's playground is the ocean space, and we operate within these areas of oil and gas, marine operations, and in renewables. And our niche within renewables is the offshore wind. We provide services such as system design for floating wind, bottom fixed turbines. There we do analysis and monitoring on cable structural integrity. We do structure and foundation monitoring, and we do vessel operability assessments for the installation phase. So how do we do it? We are not alone having a strong technology base, but however, what makes 4Subsea so special to me is how we operate. We combine know-how from engineers with domain knowledge with sensors and software. In this context, domain knowledge typically meaning engineers with background in hydrodynamics, mechanical analysis, material technology, and structure foundation interaction. We combine this with data scientists, software developers, and our in-house developed portfolio of sensors. We bundle all of this to deliver context-relevant, data-driven, and actionable insights. I believe that we're quite unique in this sense. There are few other players that combine domain, sensor, and software in one service. So today I will focus on the topic of cable and cable protection systems. So we're not a provider of any of these systems ourselves. So in that sense, we are independent and not biased. But we are frequently involved by clients to support in writing procurement specifications, design validation, method developments for analysis, and we monitor installed cable systems for structure integrity. We are also frequently involved in failure investigations, root cause analysis, and even as expert witnesses in arbitration processes. But so why should we focus on cables and CPS? Well, operators have historically had limited focus on cable integrity, but with rising cable issues, they now receive a lot of attention, giving a current high failure rate of major faults. The cable system is one of the most frequent failing systems in an offshore wind park and the most costly failing system. Arkwright Consulting research reports that the annual cost of offshore wind subsea cable failures globally was in 2021 estimated to be about 230 million euros and is assumed to increase. The amount arises from an estimated failure rate of 8 to 10 major faults per year and an average cost of failure of 23 to 35 million euros per case. As an example, Ørsted reported in 2021 that a scour protection method which left the inter-array cables unstabilized could be the potential reason for an up to 403 million euro issue across up to 10 wind farms in Europe. Cable issues have until now been the most frequent and severe insurance claim in offshore wind. And this number is expected to increase due to increasing and aging installed base. G-Cube reported in 2021, based on insurance claims data from 2010 to 2020, that cable issues account for 33% of the industry claims incurred, 55% of total claims spent, and 73% of total claims spent during operation. So what is actually causing these issues? Failures to inter-array and export cables are documented to be primarily due to installation damage and manufacturing defects. So examples could be defective design, contractor errors, defective workmanship and construction defects, handling issues and collisions, electrical failures, and others. So the efforts and resources that go into solving these issues are substantial. The total market for cable integrity towards 2030 is estimated by Arkwright to be 450 million euros, whereas 290 million euros of these are within failure identification, repair planning, services, and monitoring. So that brings us to the topic of cable and CPS motion monitoring. When we talk about monitoring of cables in offshore wind, many will usually think of monitoring of inter-array or export cable power course functionality or health by the use of temperature sensing through optical fibers embedded into the cable. But in addition, there is a motivation to address the topic of monitoring cable performance from a different angle by monitoring the motions of the cable or the CPS. So typically, offshore wind power cables are not designed for excessive dynamic movements, as they are enclosed inside the monopiles or J-tubes, or where they are exposed on the seabed, they are protected by cable protection systems to restrain motions. In design, the main assumption has been that inter-array cables are static. Still, we know that excessive cable motions is a key driver of fatigue, especially in unstabilized conditions. And given the number of turbines in an offshore wind farm might have, and the complexity of offshore operations, it's obvious that scaling effects can be significant, and thus getting it right the first time is essential. So on the slides, we see a simulation, a plan view of the monopile and the inter-array cable seen from above. The left-hand simulation is a temporary condition, and after installation, but before the cable is stabilized with CPS, gravel, or rocks. So the simulations are with site conditions, and as seen, the motions are significant, especially if we keep in mind that these cables are not designed for dynamic conditions. So obviously, this is a bit of an extreme case, but still simulated based on conditions for this specific sites in the storm. To the right, we see the same cable after being stabilized with CPS and gravel dumped on top of it. Although being significantly more stable, one can, by looking closely, see that there are some motions close to the entry point of the cable to the monopile, and even inside the monopile. So does this matter? Yes, unfortunately it does. The accumulated loads in the temporary phase drive dynamic loads, typically not considered in design. So the temporary phase can actually be quite long enough at least to drive high structural fatigue rates, which dramatically reduces service life, and in worst case scenarios, a cable failure. In this case, even the motions in the stabilized condition, although being significantly less, added up to service life less than design. So we have actually experienced that several offshore wind operators experience CPS failures due to motions exceeding design limits. So why do we need motion monitoring? Well, if you don't know, you should measure. What we do know for sure is that the actual long-term loads on your cable and CPS will deviate from the design assumptions. They will either be higher or lower. In either case, as I have presented, there is an economic incentive for optimization of operation to either meet or exceed the design lifetime. The sooner you know the actual system response, the larger is the range of available options to optimize, or in worst case, to mitigate. And the key to unlocking this knowledge is increased understanding, including monitoring of motions. Motion monitoring helps to manage risk and reduce the uncertainty of how the system behaves. It can verify whether motions are as expected from the design analysis, and even of more value, it can be used to calibrate prediction models. On the potential upside, if the motions are smaller than what is predicted in the analysis, there is a potential for lifetime extension. So knowledge of actual measured motions also enables smarter operations decisions and need for mitigating measures. For example, by identifying the need for additional stabilization or other repair solutions. And this is actually decision support in action. Okay, how does it work? Well, our niche is autonomous monitoring solutions. Why? Well, because we aim at reducing complexity in installation and operation, and at the same time, increase the monitoring system robustness. Our sensors can be installed during cable installation or be retrofittable installed either by diver or an ROV with clamps or magnetic brackets. Examples are shown on the slide. We deploy sensors and typically leave them on for a period of some months to a year, long enough to capture representative environmental conditions. We limit cabling to a minimum, something we can do since the sensors are battery driven, with approximately 12 months logging capacity and storing with a 10 Hz frequency. We use 4Subsea motion sensors as our workhorse, as shown on the left on the screen. These are 6-axis IMUs that measure motion in all 60 degrees of freedom by recording acceleration and rotational rates. The sensor is robust, fully autonomous, battery powered, and made for harsh subsea applications, field proven through years in the oil and gas industry. But raw data by itself has limited value. Our experience is that engineers spend too much time on structuring, cleaning, and quality assuring data. They lack the framework to ensure that the raw data is processed to insights, and thus struggle to produce value from it. Our strength is that after retrieval, data is automatically uploaded, quality assured, and made available for further processing and analysis on our digital platform 4Insight. So on 4Insight, the sensor data can be combined with data from other sources, such as environmental data and other data sources. 4Insight will then provide dashboards containing processed and contextualized data. In addition, we provide a suite of tools for plotting and processing of data. Less wrangling, more valuable insights. So I thought I could run through a couple of examples and case studies that we've had. So I've included 2 real examples showing the value of motion monitoring. So the first one, this is an example case of motion monitoring of a CPS on a seabed. The operator had, after ROV inspections, concerns that the CPS on the farm, that the CPS was moving more than they were designed for, and that this would impact their fatigue life negatively. The operator decided to mount ballast modules as a mitigating measure and wanted to use motion monitoring to verify sufficient stability post the installation. We designed a special clamp for this purpose, in which our sensors was mounted. 3 of the CPS were equipped with these clamps, which were attached on deck of the vessel during the cable repair campaign. The sensors recorded motions for 10 months before they were retrieved by ROV and brought onshore for data processing. And to the right, you see a snapshot of one of our 4Insight dashboards showing data from the CPS monitoring campaign. Displacements in the transverse and vertical directions are plotted together with the measured weather. in the same time period. So in addition, we have included an application calculating the accumulated distance the CPS had traveled as it rolled back and forth on the seabed. And as you can see, it has accumulated a transverse distance of 1,500 meters over a period of 10 months. And that is a significant distance. And the vast majority of this distance occurred in rough weather during winter storms. During a winter storm, particularly for wave heights exceeding 3 to 4 meters with unfavorable wave directions, which were close to perpendicular to the CPS. So conditions here were as unfavorable as they could have been. And the monitoring campaign proved that even then, with the ballast modules attached, the CPS was unfortunately not stable on the seabed, and further actions needed to be taken to obtain satisfactory stability. So this was a case of an unfavorable events, which led to some actions needed to be taken. The second case is slightly different, because in this case, the monitoring is done on the cables inside the monopile. And the motivation for monitoring cables inside monopiles can be many. For example, that the cable may experience excessive motions due to excitations from the monopile itself, or in some cases, the water movements inside the monopile will cause unwanted excitation of the cables. In this specific case, the operator was concerned about observed motions of the cables inside the monopile. And although being moderate motions, an assessment was required to understand if this could develop into a critical situation over time, reducing the service life of the cables. So remedial actions are in this case potentially very costly, as this would require work on a significant number of turbines across the park and inside the turbines, and be very complex offshore operations. The motion sensors that were attached to both cables inside several monopiles across the wind farm, mounted using tailor-made clamps attached to the cables just above the water line as shown in the illustration. The monitoring campaign was divided in 2 phases. The first one with a 3 months duration to provide some initial results, and the second phase with a round of 10 months duration, capturing the winter period. Therefore, 2 sensors were attached to each cable so that 1 sensor from each cable could be retrieved after the first monitoring phase. The second sensor could be retrieved after the second phase. The dashboard to the right shows time series of displacements relative to measured wave heights. By comparing motion and environment, we found a strong correlation, and were able to provide insights into actual movements in an area where it was very challenging to predict and calculate such effects. So the measurements could be directly used to understand and assess the lifetime of the cable. So this takes me to the end of my presentation. And to summarize, we have talked about how we can gain insights into global cable and CPS systems response through motion monitoring. The main value gained from this is an unlocked cost-saving potential through critical decision support. This value is obtained by reducing the uncertainty of system behavior, closing the gap between design and operations, and by understanding actual motions, and thereby also reducing the risk of failures. A monitoring campaign provides data-driven decision support for operators of offshore wind farms, enabling tailored mitigating actions if required, or providing basis for lifetime extension. So thank you all.
Great, thank you. That was really interesting and quite fascinating about the problems just on the cables so close to the bottom of each turbine, which I guess is your focus right now. You talked about at the beginning that there were 8 to 10 cable failures a year, I think, across, I don't know whether it's the North Sea or the Baltic or maybe the whole combined area. Obviously, cables are quite long. So do you know how many of those 8 to 10 were specifically in the bit that you're monitoring here, just at the base of the turbine?
No, I don't really have insights on kind of the number of those 8 to 10, but it's a typical area where we see that there are issues with the cables, because it's the free span section where they're most exposed to these to loads and dynamics as well. So in the cases of being kind of a dynamic failure, is typically in that area. But the number obviously is more kind of the totality of the failures that the industry sees on cables and so on. And again, there could be a number of them from manufacturing and handling and so on as well, but they all could add up to these significant numbers.
Yeah, no, I mean, I guess it's interesting because I think we can all understand that when the cable's first mounted, there's a gap between the cable mounting before they then stabilize it with rocks and the necessary bags filled with rocks or whatever they're doing to keep the cable then stabilized, in which case it's moving a lot more, and obviously that's inducing more fatigue on the cable and therefore potentially reducing the life of it. Yeah, I guess it's interesting to know how much actually times that's failing in that specific point there versus obviously other cable failures. And you get involved in doing cable motion measurement elsewhere, other parts of the cables, or is it really just at the bottom of the transition piece?
No, so it's often in that section, but also inside the monopile could be. We do also, I mean, conceptually is also kind of an issue, obviously, on floating wind turbines. So we've done some early stage kind of pilots and so on as well, because they have even more dynamics. But then at least it's the dynamics are more taken into account in the design. So for cables, it's mainly that area that we see the concerns.
And I assume your sensors are you just mount them for a period of time, and then at the end of it you collect it, and then you can analyze the data, and then it's all stored within a logger in the actual device or whatever.
Yeah, that's right. So it's kind of a full computer actually embedded into the sensor, so they both can do some processing, filtering, and so on, and they have a storing unit in each sensor, so you will never lose the data. It's stored. Even if we would be in the case the battery goes out, the data is stored there. So it's a very robust and field-proven solution, which has definitely served its purpose.
Yeah, and can you get real-time data from it? Can you plug it into a fiber optic feed if you were so minded to?
You could not by fiber optics, but you would just have an additional electrical cable pulled up to the to kind of a top side or any point where you can actually extract data. So we can do that, and sometimes we do. We even can interlink sensors, so you get full synchronized data between two sensors, which is an option. We do that quite frequently, but then obviously it produces a kind of you add some risk of cables again being broken and so on. So for the robustness, it's in a way better to just leave it as it is.
Sure.
Yeah.
Do you have any examples of cost savings achieved by following your monitoring campaign?
Well, yeah, I couldn't really go too deep into the details of the two cases we have, but it's kind of in one of the cases, actually, as I kind of go slightly into, they saw that there wasn't really a need to do any changes and alterations to it. So it's much about kind of documenting that you are fine as you are. So there's some cases where we're fortunate to do that. Other cases, unfortunately, we document that there is actually a problem. So it goes a bit both ways sometimes.
No, okay, great. Yeah. All right, brilliant. Okay, well, I'm going to draw it to a close there because we're close to finish. So thank you very much for your interesting presentation on monitoring cables, Ignacio, and we'll close the session here.
Thank you.